All right, why don't we just, there's no confidence interval in this section, but why don't we go into this a little bit more in depth, and let's do the classical approach for the same problem, right? So you have all this here. Now we're going to try the classical approach. So we have a skewed right distribution. This is the chi-squared distribution. And we've already established that the degrees of freedom is 4. Last time I mentioned that for this particular test, we're only going to have a right-tailed test. And this alpha is equal to 0.10. Here's the critical value. It's a chi-squared of alpha. If you want to throw the alpha in there, it would be chi-squared of 0.10. That's the critical value from the table. Let's see if I can find a table close here. On this distribution, this is 0. And any test statistic that falls out here in the critical region, that's going to lead us to reject the null hypothesis. And any test statistic that falls over in this region from 0 up to the critical value, that's going to lead us to conclude that we do not reject the null hypothesis. So let's go to the chi table and find this critical value. Then we'll go ahead and plot our test statistic, which from the other sheet was 9.688. All right, so from last time you have a chi table. Here you have the 0.10, and if you go down to the degrees of freedom is 4, degrees of freedom 4, and follow that over. Alpha is 0.10. There's your critical value, 7.779. So you find it in a way very similar to the way you would find the critical value on the T table, 7.779. All right, then we're going to plot the test statistic on that same scale. This is 0, and this is 7.779. Then our test statistic is just a little bit bigger than, a little bit larger, so it's going to fall over here. Maybe it's right here, 9.688. That's the test statistic. The test statistic is a chi-squared value, and the critical value is a chi-squared value. Both of them will be plotted on the horizontal scale here. If you wanted to calculate the p-value, you would calculate the area from our test statistic over or something more extreme. And you can see that the p-value, which is the red shaded area, is a little bit smaller than the alpha value, which is the black shaded region. P is less than alpha, reject. Test statistic falls in the reject region, reject. So the decision that you make in either case, it has to be consistent. This is the frequency table. These are the observed values. And it's the observed values that we put into matrix A. And then we have the conditional proportions. This is what we calculated in section 4.4. And then this table here, I ask for the expected values. The expected values are the values denoted with E in our test statistic. And we're going to put those in, or actually the calculator will put those into matrix B. So here I'm asking for all 8 expected values. And if you remember the test statistic. That's this chi-squared test statistic. And it's the sum of a bunch of fractions that look like this. You take the observed value and you subtract the expected value, square it to make it positive, and then divide by the expected value. So you're going to sum up 8 fractions that look like this because we have 8 different cells. And we get this from the chi-squared test. So here's the, the 30-second version of finding the test statistic and the p-value. Put these in matrix A. There are 2 rows, 4 columns. So you want a 2x4 matrix. You need to go to the matrix menu and then edit the matrix. 2 enter, 4 enter to make it look like that. And then type in, maybe I'll get it right this time, 40, 5, 7, 41, 30, 15, and 14. And then quit, run the test, and there's your test statistic and p-value, 30 seconds. So that you can get to very quickly. All right, here's an added step. So if you want to go to the matrix menu again, and then let's now notice that B used to be a 2x5 matrix. And after we run that chi-squared test, it's now a 2x4 matrix. So let's go to B, and then we're just going to start entering these in. 44.5, 44.5, 35, 35, 10, 10, and 10.5, 10.5. What's interesting about these expected values is that when you add the actual values, the observed values from the data, you're going to get 89. Here you're going to get 70. Here you're going to get 20. And here you're going to get 21. These values over here are set up in the same way, so that when you add those two, you're going to get the same 89, the same 70, the same 20, and the same 21. That same thing will happen over here. So if you add those numbers, 12 and is that 88, is it 100? 71, 29, 100. So I guess 200. If you added up those 4 numbers, you would get 100. And if you added up those 4 numbers, well, they're the same. So you would get also 100. The only reason why these 2 numbers for each category are the same is because we have the same row totals over here. All right, here's a problem from section 4.4. Calculating the conditional proportions and interpreting them, that's the most important part of the entire problem, because that's where you're going to see the differences. And that's what you're looking for as a statistician. What are the differences? This one asks for the classical approach. You've got degrees of freedom is 3. So you should be able to find this number from the chi table. And then here's the test statistic. It hovers out here in the reject region. So we're going to reject the null hypothesis that there's no relationship between age and communication preference. So there must be a relationship. And then here's how I wrote up that relationship. The younger cohort prefers using the cell phone and text messages more than the older cohort. And you could turn it around and say that it's not that they prefer it more, it's that they prefer it at a higher rate than the older group. So this is the chi-squared test in 12.2. And this table right here, calculating these conditional proportions, is what you're going to be doing in 4.